And it is the equilibrium constant. Now, we have talked about reactions a lot, it's chemistry, but we always assume they went to completion. Well, that means that, for example, if you take magnesium and you react it with oxygen, you produce magnesium oxide. It's a one-way reaction. Well, that one is a one-way reaction, so it only goes forward. But there are some that reach equilibrium. Well, what does that mean? That means that the reactants are going to form products and the products are going to form reactants, which means they don't go one way, nor do they reach what we call completion. They keep going back and forth. So this is chemical equilibrium, which is condition of reversible reaction where the rate of the forward is equal to the rate of the reverse. So rate forward is equal to rate reverse. Okay, and this is a dynamic condition, meaning that the reaction continues with no net change. Now, when we say dynamic, that means that it's not like a picture where you take it and it's frozen in place. So, for example, if we have a room with two doors in it and we have to maintain 20 kids in the room, or 20 students, excuse me, because some of us aren't kids, 20 students in the room. And let's say that we have 12 male, I have to write this down because I can't remember, and 8 female. Okay? And the only reason I'm picking numbers is we have 20 students total. Well, we can only maintain 20 students. But if we have to maintain our ratio, if somebody gets up and goes out one door, then somebody comes in the other door. Well, if you have a male leave, you have to have a male come in. If you have a female leave, you have a female come in because you must maintain. Now, they're not the same people, but you're maintaining the same ratio. Same thing with the reaction. They're the same molecule in terms of the same type, etc., but they're not the exact same molecule because you had a molecule react one way or the other. So the net effect is that K is the ratio of products over reactants. So we'll get into more details of why specifically, but it's a constant motion. So because equilibrium is kind of unique, it can be approached from either direction. Now, this is not the case for one-way reactions. For a one-way reaction, you can't approach it from the product side. But for equilibrium, you can start with reactants and go to products. You can start with products and go with reactants. You could start with some of both and make them level out. Now, a catalyst, which we said speeds up the reaction, if it speeds up the reaction and only lessens the time it takes to reach equilibrium. Okay, so what that really means is a catalyst is great for speeding up a reaction, and because the rate of the forward equals the rate of the reverse, it does make it get there faster. But once you're at equilibrium, catalysts have absolutely zero effect. So remember, K is equal to products over reactants. More about the specifics of that, but that's a generality. So if you have a product over the reactant, we say it is product favored. And if you look at the K, then the K will be really large because your product is the greatest. If the reactant is greater than the product, that means the larger numbers in the bottom will be reactant favored, and the value will be really small. So depending upon what your K value is, and your K can vary tremendously. I've seen Ks that we've actually used in a problem from like negative 36. Okay, negative 105 I think once. But negative something, 10, 20, 40, up to 10 to the 80, 100th, whatever. So if it has a positive exponent, it's product favored. If it has a negative exponent, it's reactant favored. So here's our equation. And notice that this is your equation. So your reactant drops, your product rises until they reach the point where they level off. So this is your dynamic condition, and they level off. So we know that the point at which they level off is your equilibrium position. Okay, so this is what a graph of this would look like. Now, I said that K was products over reactants, but that was just the generic form. Well, let's look at the details. I'm going to kind of start at the bottom. If we use anything in brackets, that is assumed that it's a molar concentration. So if I said that it is 1.2, then that's 1.2 molar. In equilibrium, you're going to find that gases, in some cases, not always, are interchangeable, but I'll tell you on that one. So that's what the brackets mean. So here's our equation. Little coefficient, little letters are the coefficients in the balanced equations. Big letters are the species. So what we end up with is, remember, we say it's products over reactants. So when we break that down, unlike in the rate laws, in the equilibrium, the concentrations are stoichiometric amounts. So if you'll notice, our species, the products all go on the top, and your species goes in the brackets, and your coefficient becomes the exponent. So all of your reactants are on the bottom, all of your products are on the top. So this is how you set up the equilibrium. Okay, so we talked about the fact that he had given an equation, and this is all 1-to-1. The forward reaction would be this rate law. The reverse reaction is this rate law. We know that rate forward equals rate reverse. Okay, so let's take it a step farther and do the math. Well, here's the same slide again. We saw with the leveling off, and now we've got it with respect to rates. So there's your reactant, and there's your product. Here's your equilibrium position. So what happens if we ratio the forward over the reverse? And these are the K values. And you're like, wait, why'd they flip? Because notice these pair and these pair. What happened? Well, rate is equal to K of A. And we'll say forward. And then rate is equal to K sub F of B, which is your product. Okay? So what we're doing is we're solving, and this is the rate forward and this is rate reverse. We're set them equal. So K sub F of A is equal to, K sub R. Can't see that as an R. K sub R times B. So if you ratio them and you put the K's on one side, so K forward over K reverse, then that means you have B over A. So that's where they get this relationship. And so since these two are constant, we can combine two constants to produce one big constant. And notice when we're doing the rate laws, this one is lowercase. See, K, big K is an equilibrium. So it's a capital K. And so if you'll notice, then the net effect is we end up with the products over the reactants. And we have the stoichiometric amounts because this particular equation was 1-to-1. So when we look at our equilibrium expression, again, if that's our equation, then we take all of our products, put them on the top, and all of our reactants, put them on the bottom. and the exponents are our coefficients. So that's how we do a K. Now, some of you may have noticed that this is a Kc. You're going to find we have Kcs and we have Kps. Kcs are concentration, molar concentration. Kps are pressure in atmospheres. Well, they can be in atmospheres, torrs, whatever, but they're pressure. More about that in just a minute to convert back and forth. All right. The Haber process. This is the first one of the chemistry put to work. And this one actually looks really, really dull. And this one's actually very fascinating. If you're into history, especially World War One and World War Two, you really need to read through this. This is actually really cool. Okay. So let's talk about our Kc values. If we have the equation, here is our Kc value, products over the reactants. Now, if we reverse the reaction, then notice what happens to the reversed equilibrium. It basically is flipped from up here. So the net effect is that if you have K for the forward, and then you reverse it, what you have is 1 over K. So what this will allow us to do is look at what we're doing to the equation. Take the K value. Excuse me, I don't know why every time I start to do these, I yawn. I'm wide awake, I just got up. But this will allow us to manipulate the value. So basically, if you manipulate the equation, you can manipulate the value. So, stepwise, if we have two steps, so we have N2 plus O2 produces NO, and then the NO goes to NO2, and you combine them together. So if you total them together, you produce this intermediate goes away, you end up with this equation here. So if we know the K's here, the question is do we know the K's here? All right. So if we added them together here, we're going to multiply the K's. Well, when we go to multiply the K's, if we have the value for Kc1 and we have the value for Kc2, we can determine the value for Kc for the new by multiplying them together. Okay? So the net effect is if you do a multiple of an equation, it's going to change it by the exponent. If you flip it, you're going to go 1 over K, etc. So what this will do is allow us to look at an equilibrium and adapt it. So, for example, for this one, we have K is equal to 20.0. All right, simple, no problem. If we look at, this is our original, and this is our new or manipulated. So what did we do to go from this one to this one? Well, if you notice, SO3 was the product, so we flipped it. That was one thing. By flipping it, we made the reactants products and the products reactants. That was one thing. Now, the other thing is in that equation, we only had one SO2. Half an oxygen and one SO3. Now we have 2, 2, and 1. So we multiplied it by 2. Well, if you flip it, you get 1 over K. All right? If you multiply it by 2, then you raise it to the second power. If you multiply it by 3, you'd raise it to the third power. So, net effect is our new K combined. And remember, another way to write this is K to the minus 1. Is K to the minus 1 times 2. So, this is K to the minus 2 is my value. So, my new K is equal to 20.0 raised to the negative 2 value. So when you do this, then your K comes out equal to 0.0025. So that's the new K value. And the other thing I want to point out is the K uses the coefficients in the equation. It uses those. But it has no unit. Unlike rate constants that have units, K's don't have. Let's do another one. Okay, so we've got this equation here. And you're looking at it going, wait, fractions! It's balanced. And yes, fractions appear, even though you were told we don't use them. We use them all the time in 1212. Okay, so here's our K value for this expression. So this K is 1.97 times 10 to the minus 20. Wow. Looking at this, this is really small, so is it product or reactant favored? Okay, because it's small, it is reactant favored. Now, the previous one, which was 20, if you're within 1,000 either way, the 1,000 to 1 over 1,000, you're really kind of one. It's when you get past that. Okay, so there's, okay, what was our point? Oh, yeah, we're trying to see what we did. So we're going to start with ammonia, which was in the product before, so that means we're going to flip it. All right, we have 4 ammonias. We only had 1 before. So everything has been multiplied by 4. So everything is multiplied by 4. So that means that your K is going to be to the minus 4, because flipping it is to the minus 1, and times 4 is to the 4th. So our new K is going to be K to the minus 4th, which is equal to 1.97 times 10 to the minus 20th. And this is where it starts to get critical. It needs to be critical that you use scientific notation, the exp, whatever function you have on your calculator, here to the minus 4th, so that you get the proper value. And I'm trying to find it. Okay, there it is. And your new K is 6.6394957 times 10 to the 78th. Wow. Which makes perfect sense because we flipped it. So if it was a reactant favored initially, it is now product flavored. Favored. 4 places after the decimal, 395 times 10 to the 78. And there's my new K value. Okay? So you will definitely have 1 like this, probably 2 like this on the exam, because they're real simple and you just need to know what you're doing with them. Okay, that brings us to heterogeneous equilibrium. So if we have this equation here, heterogeneous equilibrium means that you have more than 1 state. So we have 2 solids and a gas. So when we set up our equilibrium, we get this expression here. Now, if I told you that we're working in molarity, so that's moles per liter. So if you have a pure substance, you don't have moles. Okay, you have moles, but you don't have a volume, so you don't have a molarity. So what happens is the concentrations of pure liquids and solids are constants. They have an activity, which is the actual true value of 1. So what happens is this value is going to drop to 1, and this value is going to drop to 1 because they're pure. Now, you can have pure solids and you can have pure liquids. If you have a single gas, you can still have a volume and moles, so you still have a molarity associated with gases, which I know is crazy sounding, but if you think about it a second, it works. So for this equilibrium, there's your K value. It only involves 1 species. It's the only species that doesn't drop out. Okay. So this next problem we're going to look at, and it's 2 pages just because I broke it up. We're going to set up an equilibrium constant. And I'm going to show you 2 ways to address things, but it helps if you address things. So we have K is equal to, we're going to start with our products, NO2 raised to the 4th times H2O raised to the 6th divided by NH3 raised to the 4th times O2 raised to the 7th. Voila! Looking at it, they're all gases. Life is good. All right. Now, on this one, there are 2 ways to do this, and I've seen people do it both ways. So the first way is people look at the equation and go, wait a minute, that's a solid, so it's going to drop out. So your K is strictly silver times chloride. And no, you didn't need the bottom there. I just kind of overzealous. Or I've seen people say K is equal to silver times chloride over silver chloride. And I know that this is going to drop out, so my K is equal to silver ion times chloride ion. Now, the beauty of this is a particular type of equilibrium. You don't have to identify it yet, is KSP. And we will do KSP in this chapter. It actually appears in chapter 17, but based upon the truncated time frame, it makes life easier if I move it forward. Okay, so we have that one. So this one is a K, and it's equal to copper, 2 plus, ammonia, to the 4th. No, ammonia, not ammonium. And this is a complex, CuNH3, 4, 2 plus. Again, complexes are something that we may or may not address this summer. It's, again, part of 17. I don't remember if I threw it in. I'll have to look at it. I slept since I made my syllabus. Nothing falls out. This would be a KF. Again, you don't have to know the KSP and the KF part. Not for forward, but for formula. Okay. And here we go again. This one, again, you look at it. Oh, wait, there's a solid. So this one's going to drop to 1. So your K is equal to calcium times carbonate ion. And you're done. Because that calcium carbonate dropped out. Now, you could have written it in and put it out. This, again, is a KSP. And this one here is kind of weird because you're just dealing with water. So on the top, you have H2O, gas, and you have H2O liquid on the bottom. Now, wait a minute. We always said that gases always had a mole and a volume, so they always are in, but pure liquids are not. So this is a pure liquid, so it's going to drop to 1. So this K expression is strictly the H2O plus the gas. Now, should you write the gas here? Yes. Would you normally? No, but you're comparing water to water, so which water are you talking about? So it's important for this, but normally, no, it is not important. Okay, so within this first section, we have determined how to set up an equilibrium expression.